Okay, so let's get started. So today we're going to talk about the the maximum weight perfect matching problem in bipartite graphs, which is often called, so if you kind of look this up, sometimes people call it the assignment problem. And there's a kind of natural reason they call it the assignment problem. So the main application is basically as follows. So yesterday we talked about an algorithm where where the application was, you have workers, you have jobs. Each worker is qualified for only certain jobs, right? And you want to assign workers to jobs so that the maximum number of people get a job, right? But in this problem, it's a sort of similar type of setup, except you don't just care if people are qualified for their job, you actually care if they're good at their job, right? Which is not always the same thing, right? So the basic idea is you have, maybe you had 3 candidates, 3 workers, you have 3 jobs, and you want to assign workers to jobs. And suppose they do some sort of, they do some sort of test or something, right, to see if they're good at these jobs. So these are the test scores or something, right? And you want to assign, 1 worker per job so that you have the best possible people doing the best possible jobs, right? So and the way you measure that is you want basically the sum of all of the numbers. So if I was to pick this worker to do this job, for example, in this one, okay, this would probably be a bad choice, as you can see. But basically you want to pick these things so that you maximize the sum of the things that you pick. So you want to maximize, the sum of, I guess, in this case, if these are test scores or something, maybe the test scores over, who you sent to various jobs, right? But, all of this can be turned into a graph problem, right? So if you take each worker and you represent them by a vertex, so worker 1, worker 2, worker 3, and then you take each job and you represent it as another vertex where, it's a bipartite graph, so, you have workers on the left side, jobs on the right side, and then each edge you could label with the test score. So worker 1 is kind of got 82% or something for job 1, right? So I haven't put all the labels, but worker 3 is 5 for job 3. And then what your goal is here is to find a perfect matching. So every worker gets assigned to a job, and you want the total weight of that matching. So if you think of the edge label as being a weight, you want the weight of the matching to be as big as possible, right? So that's the setup. So more formally, so we're going to be given a bipartite graph. Well, yeah. So G with bipartition AB. And you can see this is kind of a pretty simple bipartite graph, right? Every vertex on the left is joined to everybody on the right. So, and the size of A is going to be equal to the size of B. So we're given a bipartite graph with a bipartition AB such that, well, okay, let me say, so every vertex in A is joined to every vertex in B. It's joined. Joined means, with an edge. Vertex in B. So this is just a kind of definition. This is called a complete bipartite graph. Because, you have all the possible edges, so it's, in some sense, it's complete. And a weight function W on the edges of the graph. So W maps E to non-negative real numbers. I guess we'll always assume we're mapping to non-negative numbers, right? Otherwise, I guess it'd be pretty bad to be negatively good at your job, right? So, okay, so we'll assume that the worst you can be is really bad. Yeah, I don't know. I guess people have different conventions with R+. Should this be this or should it be this, right? Because it's sort of plus to me I think positive, not zeros. Okay, zero is kind of positive and negative, right? So yeah, I think this is just completely unambiguous, right? Everyone hopefully knows what I mean by that. Okay, but yeah, I guess most people would use this to mean this, but just make sure we're on the same page. Yeah, so we want to find. Okay, so given this complete bipartite graph, you have a weight function, and for a subset S of E, so the weight of S is the sum over all edges in S of the weight of the edge. And we want to find, so the goal is to find a perfect matching, so PM, when I say, I mean perfect matching M, where W of M is maximum. So is the setup relatively clear? Okay. And in particular, we want to have an algorithm to do this. So this is going to be more complicated than the algorithm for finding the biggest matching yesterday. So I'm going to spend pretty much the whole time today just explaining this algorithm. So I don't think it's not terribly complicated, but it takes a while to explain. And by the way, so everything that I'm talking about today, you can find this in. So I'm exactly following. So there's a link to this book on the Moodle site, the book of Bondi and Murdy, and it's in section 5.5. So everything I'll say is there, and I'm going to do it exactly the same way that they did it. Okay. So here's a key kind of definition. It's going to be, so we're going to, as we try to find this biggest perfect matching, we're going to have, so it's an important thing, or a useful thing is going to be that we're going to always have a labeling, some sort of labeling on the vertices. Okay, and it's going to be something called a feasible labeling. So a function L from the vertex set, again to whichever you like, R plus or 0 infinity. So we're going to call this a feasible labeling. If so remember we have this weight function, right? So if L of U plus L of V is at least as large as W UV for all U in A and V in B. So it assigns a number to every vertex, and all we care about is that if you add them up, then it's always at least the weight of that edge. Remember, so everybody in A is joined to everybody in B, right? So I don't have to write UV is an edge or something. Okay, another definition. So again, for U in A, V in B, say that the edge UV is tight for L. So I'm assuming L is some feasible labeling if this inequality holds with an actual equality. So L of U plus L of V equals W UV. So perhaps tight for L, I don't know, with respect to W or anyway. So a tight edge is one where this is tight, where there's no slack. Okay, now here's the key theorem that makes this is going to make the whole algorithm work. This is the whole reason why this is going to work. So let L be a feasible labeling and let H be the graph B, comma, so the edge set is going to be all UV such that UV is tight for L. So hopefully this isn't too confusing, right? So this is the edge set, right? It's all the pairs where the thing is tight for the labeling, and so if H has a perfect matching, let's say M, then M is a maximum weight perfect matching, well, in G with respect to W. So if you can find if this graph of the tight edges has a perfect matching, then automatically that's the best matching for the original problem. Is that clear? Any questions? Okay, and actually this is like, this seems, I mean, to me, I thought this was kind of an interesting fact, but it turns out it's super easy to prove. It's basically just by definition almost. Also, I just want to I don't want to spend really any time on this, but I'll super briefly mention that this is sort of rooted, well, in weak duality. So I'm not going to do any of this. I did, originally intend to connect all of this stuff to linear programming, which you can do. So, I mean, if you're interested, you can read, it's in Shriver's notes. But this is essentially basically, well, maybe weak duality, maybe even strong duality. So it's basically LP duality. So the fact that we're using this word feasible labeling, it's not a coincidence that in linear programs we were talking about feasible things as well. So this labeling would be, in some sense, feasible for some sort of dual problem related to the matching problem. But like I said, let's not get into that. Okay, let's just focus on proving this theorem. So here's the proof. So suppose that M is a perfect matching. Well, there's something special about, so M is a perfect matching. So if I take the sum over all the edges in M and add up their weights, well, remember, so this is a perfect matching, so every single vertex in A and every single vertex in B is included in exactly one of these edges, right? And if I have the edge, suppose that the edge UV is included, right? Well, that's we're dealing with tight edges. So basically if UV is in this matching, because these are all tight edges, we know that L of U plus L of V is exactly WUV because these are tight edges. And every single vertex appears once in exactly one edge. So this turns out to be exactly equal to the sum over all the vertices L of V. So this is the reason here, because edges in H are tight. And it's a perfect matching, so every vertex appears once. So this is going to be exactly just the sum of all the L of V, sum of all the labels. Is that clear? But now take any other perfect matching. So let M prime be any perfect matching. And you actually get a similar thing. You get a similar inequality right away, except you don't know that the edges are tight, so you don't have equality. But you know that because it's feasible, so since L is feasible, if I just sum over all the edges in M prime and take their weights, well, that's going to be at most the sum over all vertices of their labels. Because, again, every vertex appears at least once. Well, appears exactly once, right? Because it's a perfect matching. And on every edge, you basically have this thing again, except with an inequality here. And this is literally, so the weight of M prime is equal to this, which is, no, so you see this, do you mean strictly less than here? Or no, because, no, the weights generally are less than the sum of their endpoints. Yeah, so no, it goes in this direction. And like we showed above, this is exactly equal to the weight of M. So, right, this is W of M. Okay, right, so if the graph of tight edges has a perfect matching, automatically you're done. You can just say, that's the best perfect matching. So basically everything comes down to now just trying to pick pick your feasible labeling so that you can find a perfect matching in H. So now we'll talk about the algorithm for solving this problem. So this is something which people call the Hungarian algorithm. Or sometimes, well, and it's usually attributed to Kuhn and Munkres. I'm not sure why people call it the Hungarian algorithm. There must be some story behind this. But okay, right, so yeah, so before the algorithm starts, we want to pick kind of any feasible labeling, and we're going to update it as the algorithm goes on. So how do you get any feasible labeling? Well, I mean, there's a lot of different ways you could do it. So yeah, so before everything starts, I can just let, for example, I don't know, I can say the label of V is, let's say, the max over all edges of the weight of the edge over 2 or something. Right, and then certainly, if you look at any edge, then its endpoints will add up to more than the weight of, or at least as large as the weight of the edge for all V. Right, so I just need something to start with, some sort of labeling. And we're going to, so our kind of initial matching is nothing, it's the empty set before we start. And the graph H, actually let me change this a little bit, sorry about that. Let's make this the weight of the edge plus 1, just so that we have, initially we actually have no tight edges at all. Just to, just so that now I can write this, and this is the graph of all the tight edges because there aren't any tight edges. So this is always going to be the graph of tight edges. And we'll just keep updating it as we change this assignment L. Okay, so that's before the algorithm starts. So is it clear that this L is a feasible labeling and everything? Yeah, I mean, there's lots of different ways you could choose this L, right? You just have to pick, it just has to be feasible. Okay, so now we're going to start the algorithm. So step 1, okay, initially step 1 is going to be sort of silly because, okay, so what I'm going to say is if the set, or if every vertex of A is saturated by M, oh yeah, M, by the way, just another comment here, this is will always be a matching, not just in G, but in the tight edges H. So just anyway, so if every vertex is saturated by M, then we just stop because we found a perfect matching on the tight edges and output M, and it's optimal by the theorem. Right, because it's always going to, at all steps, it's going to be a matching in H. Those are the tight edges, so it's going to be optimal. Okay, obviously at the beginning this isn't going to happen, but later it could. Okay, so otherwise, let U be any, oh, by the way, remember we're in the setting where the size of A is the size of B, right? So if A gets saturated, then B gets saturated. So then it would be a perfect matching, right? So yeah. Okay, so otherwise let U be any unsaturated vertex. So a vertex not involved in the matching. And now we're going to do some stuff. So set S to be, initially put S equal to U and T equal to the empty set. And basically what we're going to do now is we're going to kind of try to find an augmenting path. And if we fail, then we're going to change the feasible labeling L. And then we're going to continue trying to find an augmenting path. And so we're going to try, so here we're going to, this is going to, in this kind of, in the next little bit, that's going to be our goal. Okay. Because as you might remember, right, finding an augmenting path that's pretty much the only kind of, it's the main way that you can increase the size of a matching. Okay, so while T is a strict subset of, so I'll explain this notation. So this is NH of S is the, where did I put that? So this is the neighborhood of S in H. So what do I mean? So formally, this is the set of all, let's say, I don't know, Z in V minus S such that there exists X in S such that they're adjacent. So it's the thing, all the things you can reach. So XZ is in the edge set of H. So obviously, I don't mean the edge set of G because remember, G is kind of a boring graph, right? All the edges from A to B are in G. But I mean, so this sub H means that I'm talking about the neighborhood in H. So while this holds, do the following. So, yeah. E of H is the, yeah. So at all times during the algorithm, E of H is always going to be the set of tight edges for the labeling L. Ah, yeah. E of H, yeah. I see. What this, yeah. I sometimes take for granted the kind of graph theory notation because, yeah. So this is the edge set of H. But thanks for pointing that out. So this is just all the things. So if you look at S and you look at things outside of S for which there's an edge going to them from S outwards, you know. So if you have S and H of S, it's just the things for which there's at least one edge, and these are edges in H. Okay, so as long as this is the case, so if T is a strict subset of the neighborhood of S, we can always pick something here which is not here. So we can choose Y, which is in NH of S minus T. So sorry. But anyway, we're just picking Y, which is here, but it's not in here. Okay. And now we're going to see, I mean, kind of in one case, we're going to say, oh, we found an augmenting path, and we're going to increase the matching. And in another case, we're going to keep on updating the sets S and T. So let me explain what I mean by that. So, okay, so certainly if Y is saturated, then we haven't found an augmenting path, right? Because the endpoints of augmenting path have to be unsaturated. So the first case is that Y is saturated by M, right? And in this case, what we do is we pick Z such that, so since it's saturated, we can choose Z so that YZ is in M. There's some matching edge containing Y, so maybe it uses Z. And now we define, so we let, well, I'll say add Y to T and Z to M, or sorry, to S, and we go back to 4, right? So, yeah, so then we go back to 4 and we check, is it the case that T is a strict subset of this? And if so, we go back into this thing. So we kind of loop around multiple times, possibly. Now the second case, so sometimes it might be the case that you've picked this Y and he's not saturated. So I claim that in this second case, so kind of by how we constructed S and T, so we get an M augmenting path from the original guy, U, to Y, and we swap it by, changing which ones are in the matching and which ones aren't to get a bigger matching, which we'll also call, when we get the bigger matching, we'll also call it M, and then we go to step 1. Okay, let me explain why, just at least give you a picture to convince you that you get an augmenting path. So I perhaps won't prove this formally, but I'll just give you a sort of example to see how this part of the algorithm goes, and how when you find this non-saturated guy, how you get an augmenting path. So say that this is A, and this is B. This is my original vertex U. So at the beginning of step 4, I've got U here. My set S is just U, right? And T is currently the empty set. And then the first thing I do is I look, does he have a neighbor in H? And if he does, I pick it, right? So perhaps I'll call this guy Y1, because there's going to be a lot of Ys at every different step, right? Okay, so maybe when I choose this neighbor, maybe he's saturated, right? That might happen. So if he's saturated, then I find a matching edge containing him. So this is in M, and I find this vertex Z1. So and now I add him to S. So S increases to have 2 elements, and I add him to T, right? And now I keep going. So I look at this set S, and I say, does anyone have a neighbor here that I haven't already looked at? Like, does anyone have a neighbor who's not already in T? And if somebody does, so maybe U has another neighbor, right? Another neighbor Y2. And we say, is he saturated? If he is, we again find another matching edge. We find a vertex Z2, right? And now T increases, S increases, right? And we check again. Does somebody have a neighbor who I haven't seen yet? Maybe Z2 does, right? Because I'm looking for, it doesn't have to be a neighbor of U. It can be a neighbor of anyone in my current set S. So maybe it's Z2. I call him Y3, right? But maybe at this point, maybe we've finally found an unsaturated vertex Y. So suppose he's unsaturated. But basically now we can kind of go back through this whole construction to find an augmenting path, right? We can go from Y3. So he was added. We look at his neighbor in S. Well, why was he added? So either he's U, which we would just add that to the matching, or he had a matching neighbor back up here. Well, why did he get added? Because he was a neighbor of U. So this would be our augmenting path from U to Y2 to Z2 to Y3. Right, so in that case, we've increased the matching. We go back to the beginning. We check if it's saturated, if everything in A is saturated. If it is, we just win. Otherwise, we go through this whole process again. Okay, but it's not clear. I mean, maybe you never find an unsaturated vertex, and that's the other case. So possibly, you go through this whole kind of while loop, and maybe at the end of the while loop, you just have T equals the neighborhood of S, and then you end this loop. Okay, so after this, and that's the case where we're going to change the function L. So we'll call this 5. So if we escape this while loop, so now we have that T is the neighborhood of S in H, right? Because I'm assuming we haven't gone back to step 1. We've escaped this loop, and so now we modify L as follows. So we let alpha be the minimum over all x in S, y in B minus T. Okay, if you think about it, so the set S is always going to be contained in A. The set T is always going to be contained in B. So this makes some sense, perhaps. So the label of x plus the label of y minus the weight of xy. So this is sort of the surplus, on the edge of the labels versus the weight on that edge. And note that alpha is positive because no edge from S to B minus T is tight. This is because T is literally the neighborhood of S, and H is the graph consisting of the tight edges. So none of those edges are tight. And that means that alpha has to be positive, right? You can't have any of these things being equal. Okay, so we're going to modify the labeling L. So change L of V to, so there's 3 different cases. So we're going to make it L of V minus alpha if V is in S. So So it's going to be L of V plus alpha if V is in T, and it's going to not change if, well, otherwise. So everybody stays the same, except everybody in S has their label decreased by alpha, everybody in T has their label increased by alpha. Okay, so some observations. So first, the labeling is still feasible. Now, if you think about, that's because, so what does this mean? Feasible means that your sum of your labels has to be at least the weight of the edge between you. Basically, if you think of where the edges can be, so an edge from S to T, certainly, one vertex decreased by alpha, one increased by alpha, the sum is the same. It cancels. So the sum of these weights is the same as before. Somebody from S to B minus T, right? Well, we decreased by just alpha, and that was defined to be like the minimum of the kind of surplus between, of all of these edges, right? So these ones are still fine. And any other sort of edge, well, okay, this edge is certainly fine because we increased one of the endpoints, and we didn't do anything to the other one, so it became even more happy. And this sort of edge, well, nothing changed, so it's still feasible. Second observation is that every edge which was tight before is still tight. Actually, that's not quite true. So except, yeah, this sort of edge won't be tight. So except, it's going to work. Except possibly edges. This is going to be fine. So from A minus S to T. But that's going to turn out to not really matter. But right. And the third thing to observe is that there is now a tight edge from S to B minus T. So originally, remember, like before we changed things, the neighborhood of S and H was just T, right? So all the tight edges from S went to T, but now we get one going to B minus T. Because if you look at the pair, so remember how much we decreased things by, right? We decreased everybody in S by alpha, and so if you take the vertex X and the vertex Y, where this minimum is achieved, that's now going to be a tight edge, right? It wasn't tight before, but now it's going to be tight. Okay. So I think we're 1 minute over time. So I'll just briefly say what you do at this point, because we are done in the algorithm, although I won't be able to explain completely how everything works now. But what we do now is update the graph H to include the current tight edges, right? Because the set of tight edges has changed now, and we go back to step 4. Go back to step 4 where, now it will be the case that the neighborhood of S is bigger than T, or it strictly contains T because we have this new tight edge. And then we go through this process again and try to find an augmenting path, and so on and so forth. Okay. And okay, that's good for today. Thanks.